We do quite a bit of introduction. Today we cover function call for our lecture 12, part 3 of the assembly. This is just so that I can post it on YouTube later. Uh, if you look at how function call is done, right, what has to happen? First of all, your code jump around. You jump to another function, right? So let's say you have function f1 and f2. Right, F1 and F2, what can you do? What are the calling that you can do within F1 and F2? If you are from F1, which function can you call? You can obviously call F2, right? And if you have recursion, you call F1 with a different input, right? So you can call F1 again. F2, same here. You can call F2, you can call F1. And as you can see here, the code jumps everywhere, right? It jumps from F1 to F2, jump from F1 to F1 again, jump from F2 back to F1, depending on where, basically depending on how you write it. The programmer are God. Think of it this way: to the computer, you guys are God. They'll do exact same thing as what you tell them to do. How do we do that? Another thing that you have to figure out is, well, function take input. Right? So you call a function, you pass in inputs, you take output. One unique thing here is when you pass in the inputs, you're actually passing the data around. You throw, like, let's say, for example, you call fifth of 5, right? Fifth of n, when n is 5. You say, hey, I'm counting fifth, I'm throwing the number 5 there. Take it and process it, right? So you pass in the value. Once you're done, you return. Fifth of 5 is 5, if I recall correctly. Then you return the number 5 back. Yay, I got the data. Right? So you can resume and continue on with my function call. The next set of things that you have to figure out is like, hey, you have malloc. Somehow you call a function, the function called malloc. Right? You need to expand your memory because you want more address for your data. How that is managed. So these are the topics that we're going to cover today. And the first thing is, let's go through something I love. The function to the right, function p and q over here, right? And as you can see here, p called q. What does q do? Well, q take I, do something with I, and return this. I'm not even going to declare what I do here, just dot, dot, dot. At the end of the day, I'm returning v of p. I don't care what is v of t, I just want to return that back. These are general things that will happen when you have function call. First of all, when you call Q, right? When you call Q, you basically tell the program, hey, jump to Q, right? Remember our assembly code, you have the label for Q. So you basically call Q. Literally, the instruction is called CALL, which is call. Call that function, right? You jump to Q. What happened? Basically now program counter, remember our program counter, right? It points to the current line you're running. Basically it tells the computer, hey, run this line, then run this line, then run this line. So you jump to kill. Anyone want to figure out, like, basically with this, how do you go back? How do you go back to that line? Basically this exact line right after you call the function, right? So there has to be a something that you have to do in assembly to make sure you can jump back to the function you call. So that's one thing. So that's the first thing we're going to cover. This is called passing the control. Why do we call control? We control the program. We control go from here to here to here to jump here. That's why that's why we use the word control. Whenever you talk about control in the program sense, it's how you control, you move around the program. You go from this line through this line, then jump calling this function, then go to this if else, then go back to loop, come back again. These are how you control the movement of your program. Then after you're done with the handling the control, next thing you have to handle, how do I pass data, right? How do I make sure Q take the value X and at the end return V of T into Y? So we'll cover that next. Afterward, we'll handle memory management. For example, if you have V of 10 like this, right? How do you actually make sure that, hey, V of 10 is allocated? Because when you declare V10, by default, it's the same as malloc. Int, size of int multiplied by 10. Same thing. But you call int V10, right? So basically, this is allocation inside the function call. We'll cover how this is done. And everything here is implemented with machine instruction. What do I mean by machine instruction? These are the ISA, the x86 assembly that as we know it, right? Basically, it's defined. It's just a pattern that if the computer sees this pattern, it will perform this task. If it sees this bit pattern, it will do add. A different bit pattern might be doing multiply. So it's a series of these bits. And machine instruction also includes another part where you implement the application binary interface, which is the choice that allows the application, that's what we call application binary interface. What's interface? Actually, can someone tell me what's the definition of interface? I think that's pretty hard to do in like human word, right? But it allows you to communicate. Right? It's something that allows you to tell, hey, do this, do that. It's the interface between two things. Application is the program you're running, right? It's an interface to connect the application to the binary. So that's why we call it API. And in x86, which is all the machine you have here except for that thing, because I think that's ARM. On the basically all the iPads you're using is ARM processor. Function call in x86 is something we learned in this class. Why do we care about function call with x86 as the first thing? So it's on most of the laptop, desktop, and server. So most of the time you need to access assembly and packet. It'll be something like a server code crash. You have to kind of like cry on the side a little bit before you go in and like, okay, I'm gonna read this assembly code and fix it. By force, most of the time you don't want to do that. But the reason why you have to understand this is just in case sometimes it actually happened and you have to know what's happening to your program. Segmentation fault, for example, you can deassemble what the code is doing and see what's wrong. But easier to use GDB, right? And then we will talk about how do we pass the control, how do you pass the data, and how do you manage the local data. So the first thing I have to talk about is something called a stack. Anyone heard about the stack overflow? You'll use it during the midterm, I guess. I mean, I don't care. I mean, it's all open book, right? So you can use it. So the reason why we call a stack overflow, when the name of the website is kind of stems from this x86 stack. It's like a stack structure. What does overflow mean in English? It's like more than what you can handle, right? It's just overflowing. So if you now, I'm gonna talk about the stack, and then you get what the overflow means directly after we talk about the stack here. x86 stack is somewhere in DRAM. So you have DRAM here, right? The stack is somewhere in there. You can allocate more things. Basically, you can expand your stack. And at some point, the stack has a limit. Stack overflow means that you allocate more than you have. So it overflows. Most of the time, it will crash your program. Hey, you allocate too much, I'm going to crash you. Or it returns when you call malloc and you got null. Right? A malloc can return a null. It means that I cannot expand my stack anymore. I can't allocate. I don't have the space to do it. If you have 4 gigabytes of DRAM, for example, you might run into this more often than another one of your friends who have 16 gigabytes of DRAM. Sorry, making that joke. So here is the overall structure of your stack, right? This will be what it looks like if you kind of like somehow magically can zoom into your DRAM and visualize how the OS organize the data and your program. So there's a region for sure for your code, right? As I said, that program are data. So the programs that you run will be on DRAM. There's another region called a stack. The reason why we call it stack is because it works like a stack. What is a stack? It has push and pop, right? We push things into the stack or pop things out of the stack. By the way, any questions so far? No?
Yes. So like for example, if I run the code at the first time and then I just run another command and do that stack of like x86 structure.
Yes. Yeah, so each function call will make a different stack that go on top of your old stack. We will visualize this toward the third half of this class. So here's like a zoom-in version of the stack. Remember our register files that have RAX, RBX, RCX, RDX, and all those R8, R9, R10, right? The register you can use. That's one of them that has the name RSP. Now, this is a special register. What it does is it stores the top of your stack. The stack has a top, right? It grows from the top, it goes up. So that's where RSP is pointing. It's pointing to the top items in the stack. Whatever value is here will be pointed by RSP. And the stack button, right? There'll be a button, but that's basically that's the end of your stack. Great question. It's kind of like the convention in x86. It's just how it's defined. So the bottom start at the high address. For example, this can be address 1000. And you go down to 999, 998, 997. It go down. Basically, when you push something in, the address keeps going down.
So it's like of the normal stack.
It's kind of like the inverse of the normal stack, and this is how x86 manage the stack. Right? It's how x86 manage the stack. The region of memory that are managed will be done through push and pop. If you push things in, you pop things out, and it grows toward the lower address 1098, 997, 996, 0. What happens if you go beyond 0? That cannot go beyond that, right? RSP will point to the top. It will point to the lowest stack after. So let's say you push Q. Source. What is source? It can be RAX, register, like one of the registers. Say, hey, I want to push RAX into my stack. You can say push Q percent RAX. You push the value RAX to the stack. So let's say you want to push that value. Right? What will happen is the first thing, let's say this value is floating in the air. I want to get that and put them on the stack. The first thing I have to make sure it happens is RSP is at the top, right? It's some value, so you can't put it there. It's already used by someone else. The first thing you have to do is decrement RSP so that it points to the empty space. So it's first it points to the empty space. Then you just put the value there as I showed here. Any questions so far? This basically is what push is doing. Decrement RSP, push the value in. That's it. That's what happens when you push.
So every time we add this stack, so it will be a pointer everywhere that we assign by push.
So the only pointer that matters is RSP. Because when you look at the stack, you don't care about what's in the middle, you only care about the top item. Right? So that's why you only care about RSP. And this simplifies a bunch of things. First of all, if you need to point to multiple places, how many registers you have to allocate? Quite a lot, right? With this, well, assumption of the stack, I don't care about everything else except for the top item. Why don't I just use one register? Cheaper. when you design a CPU, when you design any piece of hardware, one of the main trade-off is how much does this cost? This is cheap, awesome, right? I can buy my CPU with the way to maintain the stack only with one register. It's cheaper. I like it, right? It works. If I want to pop the stack, which is something I just showed here, right? The first thing is, well, as you can see here, when you pop, the value is at the top. So you take the value out, then you you increment RC so it go up. So it go up to the next top, right? Basically, you update the top item. And one quick note is, well, when you pop the stack, it's not like you delete the value from that location. Anyone want to guess on why we don't have to do this?
You just push it on, and computer don't know that okay, you want me free or not.
So somewhat like that. So let me rephrase, right? The reason is you don't have to get rid of that value because the top already gets incremented, it's already updated. So that value is not going to be used anymore. And when you push it the next time, it will get overwritten. So who cares? Because it will get overwritten the next time you push it. There's no need to go and get rid of that value. Why there's no need? It means that if you have to get rid of the value, it means you have to go to the memory, the stack is in my DRAM, and say, hey, write 0. Write 0 takes about 12 nanoseconds. You can do about 30 acts with that amount of time. Right? So I mean, save some time, right? It's basically save some time. The same analogy of like you don't have to delete this value. Anyone own a hard drive or SSD? I mean, everyone here owns a hard drive or SSD, right? When you delete a file, it's not gone. It's there. You just update that, hey, that file is not valid anymore. You don't have to, you cannot access it. You don't actually overwrite it until you have more files on your computer, and eventually it will get overwritten. Right? That's sometimes when you accidentally delete something, you can go to like a shop that would have the tool to recover those files because it never gets deleted. So the same concept applies here. All right, so that's it for the stack structure. Any questions? Or, I mean, let me know if I need to explain it again, right? I don't mind. I just want to make sure it's clear. You don't understand which part? Everything. Okay. So, it's totally fine. So let me go back to push and pop, right? So, or should I go back even further? Wait, let me go back even further. I look at you and like, I want to make sure. Yeah. Since x86 stack. Okay, here, right? This is so okay. Let's say your code has a malloc. Let's say your code has a malloc, right? You want to somehow allocate additional data for your function, right? One thing you can do is to grow the stack, saying, "Hey, I'm gonna allocate. I move my data on this portion of my memory is on the stack." So you can grow it, and then when you're free, you get rid of that. What else can you use the stack for? For example, let's say you have a function call. Let's say you have a function call. If I jump from F1 to F2, to be able to get back to F1, right? To be able to get back to that exact line, you need to save that exact address for that line on my stack. Otherwise, I'll forget where to go back. Seriously, like I go to F2 and then, hey, I don't know where to go back. I just continue running, which is wrong. Yeah, you got lost, basically. So you can use the stack to store that like pointer back to the function you just called. Okay? So that's the purpose of having the stack. And because the way stack works, you have push and pop. Push means you put in one item on the stack. Pop means you take it out. So the way push works, well, first of all, with x86, instead of stack going from 0, 1, 2, 3, 4, 5, somehow you start from the high address, say 999, 998, 997. So the top of the stack is the lowest address and the bottom of the stack is the highest address. So that's the assumption basically. It's an assumption made by x86 processor. Are you still with me? Okay. Then the next two things we have to cover with the stack is how do we push and how do we pop, right? To push, it means that you update the top, you put in one item, and that's it. How do we do that? When you push, right, you have a value you want to put in the stack. So the first thing is you update the top because the top need to point to the empty slot where you can put the value in. So that's the first thing you do. The second thing you do is to grab that value, basically plug them in the stack, as I showed here. So that's push. Any question about push? We will talk about how to, what is this for in a bit. Basically, we will have a bunch of use for this. The reason why I have to talk about stack first is because we will talk about how to use it. So that's push. Pop is basically the inverse of a push. So you want to pop, that's a value you want to pop. So the first thing you do is return that value. Return the value. And then now that because you are not using that top anymore, so you need to update the top to the current top, the new one. And that's it, that's top. So any question on push and pop? Yeah, that's all. So that's all for pushing and popping. Any question from the online folks? There's 16 here. So I guess there are 2 people online. The rest are in the room or something along that line. Just trying to figure out how many are actually online. Because there are some users using the whiteboard as well. If I'm desperate, I'm going to use the whiteboard. And if I need to repeat anything, feel free to let me know. Right? I don't mind. I'm allocating time for that. That's why we have 2 hours. So the next set of things is x86 function call. And we'll cover each one of them one by one. The first thing is, well, we have to manage the program counter, right? Can anyone tell me what's a program counter? It points to the current line in the program that you run, right? You tell, because program are data is in DRAM. When you run through your whole program, each line is a part of the assembly code. So the program counter points to that line. So the first thing we have to cover is how to manage that. One thing I need to make sure you're aware is right now we're learning x86. So when you convert to other ISA like ARM, for example, with the Apple iPad or iPhone, or even probably a device that controls this like air conditioner, they have a different ISA. They might have a slightly different way to manage how this method to pass things around. Everything will be listed out in the manual. If you read the manual, they'll say specifically how they pass the control, how they pass the variables, and how do they manage the local data. What you're gonna learn is for x86, which is Intel and AMD processor. I just throw you a bunch of code sample. We do it one by one. Forget about the assembly part and look just at these 2 functions. What do they do? Someone tell me what is the 2 functions doing? Multiply the 2 numbers, right? And then somehow return it through the variable called destination, right? So this is what you return at the end. The function called mul2, which is just doing the multiply. let's first forget about how does it take inputs and return values and only focus on how does it jump from this function to mount2, right? So you first see, hey, this is the address of mount store, and this is the address of mount2, right? So when you are the line that happens, right? You forget about the rest of the assembly code so far. Look at this assembly code, focus on that one line. It called the function that literally that's the command, call q. Call that function. This is the address of the function, right? So you call that function, you have a mount2 function defined right here, right? This is the same as jump, but it jumps as well as making sure you can jump back. It will make sure it can jump back. How? So any question so far? Basically, it calls this function, and somehow once you're done, you return. That's the return. And when return is called, it will resume on this line, the next line. All right. As you might see here, there's a procedure called call, and you put a label, right? Mount2. Then there's a return, right? There's a return, and somehow it can jump back to the exact line that you just called the function. The way you do this is done through the stack. When you call a function, this is actually what happened. Call consists of two sub-operations. The first operation is I push the return address on the stack, then I jump to the label. If you go back to the code, when I have this call queue, I have to return to 549, right, which is the next line, 549. So what are the numbers I push on the stack? I put the exact line I want to return to. So what's the number? Who thinks it's 544? There are two choices right now, 544 and 549. Who thinks it's 544? And who thinks it's 549? All right, brain freeze. No one thinks right now. It means that you guys are confused. So how can I help? All right, so to be able to return, right? It means that somehow I need to get back to 549. I need to get back to 400549. What makes the most sense? Put 400549 on my stack, right? So when you do call kill, the first thing the computer would do is, if you have a stack like this, right? Then 400549 will be here. Will be on the stack. And you call the function. Why do we do this? We know after you hit return right here, you can look it up. Hey, where do I have to jump back to? Oh, okay, 400549. I'm going to jump back to that. Basically, it allows, right? It makes the assumption that I'm going to push that particular line so that I can jump back to on the stack. And when you return, I would do a pop, which guarantee is going to be that address, and I'm going to have to jump back to. And you jump to that address and match it, right? You can jump back that at the exact same line. All right.
So what about we jump back to the original function and then we save the value of the return and be able to use for the next time? Is it possible?
It is possible. We're actually covering that next after we cover how to jump back and forth first. So here's the like cartoon example, right? So let's say the stack pointer is at 120. We are at this line. We're at this line, 544. We are at 544. This is right before we call the function. This is right before we call the function. This is instruction pointer, which is again 400544. We are at that line. We are about to execute call queue 400550. When you have call queue as we said, the first thing we do is push this on the stack, right? Then you update this. So what should be the number? What's 120 minus 8? Right? It's a hex number. So 120 minus 8, 118. Right? So if you, basically as you can see here, right? 118 will now store 549, which is where we need to jump back. You update RSP to 118, right? Because you just push. When you push, you update RSP. And now because you call this function, RIP is at this line. Right? Any questions so far? All right, and are you guys with me?
Yeah.
It's okay if you're confused. It's totally okay. I just want to make sure everyone understands. Anyone have a question? Okay, perfect. All right, so let's say I run that function to the point I'm returning, right? I'm returning this function. RSP is here. Function pointer again point to return Q. Right? When I return, how do I know where to return? Well, I look at this address, which is pointed by RSP, right? And say, hey, what's the address? 400549. 400549. So when I return, there are two things I do. You jump to here, you jump to there to make sure you can jump back to this line. Right? The next thing I have to do, increment this. Well, I guess to update the stack pointer. Right? So afterward, now I go back to 120. The program counter is at the correct line, right? At the correct line. So you can resume your program and keep running. You finish a function call, yay, right? Any questions so far? Basically, we just finished how do we have function call. The next thing is how do we pass around value, right? You have inputs and you have outputs. So this is the assumption. What we have here is what we call the calling convention. The calling convention means that someone is either the function that calls something or the target function has to make sure the first 6 arguments of your function, let's say your function is something like this, f of int a, int b, star c, A has to be in RDI, B has to be in RSI, C has to be in RDS. It's just the assumption that every single x86 processor would make is predefined. This is how x86 would treat the first input, second input, the third input, the fourth input, fifth, sixth input. RDI is the first input, RSI is the second input, RDS is the third input, so on and so forth. Then the return value would be in RAS. So before you call return, make sure whatever value you want to return, you make sure the assembly code write it to RAS. Whatever function that calls this would know, okay, that's my return value. Any questions so far? This is just like a predefined guideline that you have to make sure the first argument is stored in RDI, second argument has to be in RSI. Who is responsible for doing that? Either you as a programmer, if you want to program directly on assembly code, if you compile your program in GCC, for example, use GCC your C file, right? And let's say function f call function g, f call g. In this case, f will make all this happen. F will handle the input, g will handle the output. So the RAX part has to be done by G. The preparing A has to be in RDI, B has to be in RSI, C has to be in RDX, has to be done by F before we call the function. All right. So the next question you might have is, what if my function takes like 10 inputs? You have an inefficient function. Let's not call it inefficient function, but it's a big function. Take in 10 different inputs. Input number 7, 8, 9, and 10 will be on the stack. Basically, you push. Everything will be now on the stack. We will show an example through that, through one example in a few slides. For now, this is a calling convention. It's kind of like the assumption that everyone makes, right? So here is more example over here. Okay. So you have the mouse store, right? That has X as an input, Y as an input, Z as an input. This is the same code as we showed earlier. It called this function, which has X and Y as an input into A and B, right? Anyone remember from earlier slides which register would have the value X? All right. No, just the register name. RDI, right? Over here, RDI. So in assembly code, you see that X will be in RDI. Y would be in RSI, just is in RDX. This is what you can assume. Once you are in this function, you can always assume it's guaranteed. The first input will be in RDI, the second input will be in RSI, the third input will be in RDX, right? So you call this function. Notice, right, the first input, X, is used as the first input for mouse 2. So at this point, what's in RDI? X, right? And A, the variable A is the same as X. So it's also in RDI. So if you look at the assembly code for this, A is in RDI, B is in RSI. Right? If somehow, instead of calling mouse2 xy, I call this mouse2 yx. I want to throw whoever take my code and somehow get confused, right? Over here, what do I have to do? What do I have to do here before I call the function? Right now, x is in RSI. My bad. X is in RDI, right? X is in RDI. Y is in RSI. When I call the function, I want X in RSI and Y in RDI. I just flip the order. So I need to make sure I did flip that order. I add the code to actually flip that order. So when I call mouse2, A still takes the correct value. A should be in RDI. B should be in RSI. So this function is responsible for preparing the input. You just need to make sure the function mouse2 will have RDI store A and RSI store B. Any questions so far? Anyone confused? I don't mind explaining again. All right. So forgot about one thing. Mouse2 return F, right? So right at the end, you need to make sure F is now stored in RAX, which is actually this one. You write the program to make sure RAX takes the return value. That's it. You don't have to do anything else, because once you return, the function that calls this, it knows that, hey, this is the result. We will be in RAX. It's guaranteed. That's why we call it calling convention. It makes the guarantee that, hey, whoever writes that function, the value will be in RAX. That's how you handle the return value. And that's it. That's basically how you pass around data. So if you write a program that doesn't have memory allocation, this is basically how you can write code, right? Make sure the first input is in RDI, second input RSI. I forgot the rest actually. Go back to that table. And when you call the function, make sure RAX is the return value. That's it, really. The next set of things is how do you manage local data, right? Data inside a function that are used and allocated. A quick overview again, we use the stack, right? The stack that we established how it works earlier. And C or Java is a stack-based language, right? So when you have recursion calls or function calls, it grows on the stack. What does it mean? The stack basically stores any local things that relate to the function. Things like local variables, arguments, return pointer, all those things will be on the stack. And every time you call a function, you expand the stack. Keep growing, 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 right? So when everyone needs to use the stack, let's say you have 10 programs written in C, what will happen? Everyone, those 10 programs that are running, use the stacks, right? So each one of them has to have a discipline. Otherwise, it's chaotic, right? Your stack can grow into someone else's stack. And vice versa, someone program can grow into my own stack. Yay, right? So you should not have that happening. So each stack has to have a discipline. First of all, you call a function, you allocate the stack. When you return, deallocate that. Get rid of it. Otherwise, at the end of the day, you call like say 1,000 functions, you run out of memory. So let's say you call 1,000 functions, but you actively only use 3 at a time. Your stack should only have just for those 3 functions that you actively running. And a stack is allocated in what we call a frame. So that's a definition. A frame means this is a stack only for this function call. So let's say I call F1. The frame for F1 is defined in this region. If F1 call F2, it will grow the stack and be in this separate region. This allows 2 functions to make sure they don't touch each other and erase someone else's data. Okay. So any questions so far? Before we go through this code that has a really confusing name for the function call, which I regret a lot. So the code is like this. There are 3 functions. You, who am I? You call who? Who call am I twice? I should change the slide next time I teach this part. This is like because every time I struggle to like pronounce all this thing. Because it's basically what happens. You call who then call am I twice, and am I has a recursion called am I again. So your call chain is you, who, am I, am I, am I, am I. Right, so 1, 2, 3, 4, 5, 6. That's the chain of events, right? 1, 2, 3, 4, 5, 6. All right. So here is the so you see this is a chain call, right? You have a bunch of function calls inside each other. So it has to manage a stack chain. What are the content of each thing here? I introduced one more register. Our old friend RC, and then one new guy, RBP. What is RBP? B is for the base. P is pointer. Is a stack pointer, I have the base pointer. We have a stack frame, right? Stack frame for each function call. A stack pointer point at the bottom, the base point at the top. So it knows that this function call has the allocated region between this and this. You use the base as the top part. SRSP, the stack pointer is at the top. the part that keeps growing. So the management, right? Every time you call a function, someone has to manage the data. Why? Imagine this case. Let's say you have 16 registers, RAX, RBF, R8, 9, 10, 11, 12. What if I have a function call that uses 16 of them? Hopefully it doesn't crash, right? Obviously you don't want to make, oh, think of it this way. What if I say, hey, your program in C will crash if you define more than 16 variables? You kill me and I'll kill myself, right? Because I mean, it's hard to only have 16 variables to manage, to write a program. The program will become literally probably like a lot more useless or a lot more inefficient, right? But at the end of the day, you only have 16 registers. So let's say you have a function call that uses all 16 of them. And that function call, because it uses all 16 of them, it means that whatever value that the other function that called it earlier, the old value will be all gone. Right? So you have function f. This is RAX, RBX, and all those things, right? It uses RAX, RBX, RCX for computation and say, hey, I have a function call, I need to call G. And G use everything. Like G is like, hey, I'm going to use all the variables, RAX to R16. What will happen to these values? It get overwritten, right? It literally will get overwritten. So the way you avoid that is save them on the stack. So you can use the stack to save these variables. Okay? So you can use the stack for many different purposes. This saving part, I can guarantee you that once you're in embedded system, you want to program like microcontroller for say the ACE, the elevator, you might end up into an ISA that only has an 8 register. That's something smaller because it has to be simpler, right? It's a small chip. So you have to think about, okay, what do I save and what do I use? When you call a function, there is a caller and callee. In here, f call g, right? In this example, f call g. F is a caller, g is a callee. G get called by f. So when you call a function, the caller set up everything. The callee would finish up, so it will wrap up everything. Analogy is I need to use this room for the lecture, right? So let's say I need to use the room. I am the caller. I will come in and set up a room. Somehow I call a different function. Another person comes in, need to call the function. I set up the room for him. When he is done, he has to clean up the room for me. So that when I'm back using the room again, it has to be the exact same setup. Okay. So the callee finish the code, the caller set up the code. Here's an example. The same thing, you, who am I? Again, confusing name. Sorry about that. Regret this very much. So you are at the topmost part, you. The only function you call is who, right? So here's the base pointer and stack pointer. You call the function. The stack pointer will get updated to just the frame that's responsible for the who function. Why do you care? It makes sure that when who is running, everything in here in this region between RBP and RSP is set up by who and used by who. Then MI come in. So you allocate another stack frame. You use RBP and RSP again. MI will be responsible for managing everything in this region. It's responsible for managing everything in that red box. Again, 3 times, right? So basically you call MI. RBP and RFP will be updated to the one you run. So right now you are in this function call, right? So you run the MI function right now. The RBP and RT will cover the region of the function call you're currently running on your CPU. And let's say you're done. When you're done, you update the RBP and RT again so that this thing points to here, this thing points to here. Like this, right? And let's say you're done again with the second function call, so it gets updated to here. Another function call done, so you update it to here, right? Another function call done, so you update the stack frame back to here. Oh, sorry, I forgot you have another function call. Let me clean it up. Okay, so now you finish with the first MI, you are calling the second function MI, right? So you call the function again, so you allocate the stack frame, update RBP and RFP. MI will keep running. Once it's finished, you go back to the who stack frame. Then when who finished, you go back to the U stack frame over here. So that's the example when you have nested function call. Function call within function call within function call within function call. Remember our Fibonacci code where we use regression, right? And at some point we go and got stack overflow. I think at around 45. Look at this and look how fast it grows, right? So because I don't want to like mess up the screen here, I'm gonna draw it on the board. I think folks here can probably see this region, right? So let's say I do fib of 45. Here. What is fib of 45? Fib of 44 plus fib of 43. What is fib of 44? Well, now right now is you're calling this function first, right? And then you have to call fib of 43. But because program CPU can run one thing at a time, to first go to fib of 44. This is fib of 43. 43. Then 43 will call fib of 42, right? 42. Blah, 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 blah. Let's say this is fib of 1. And that's it, right? For this branch. This long branch of like 43, 44, 42, 41, 40, blah, 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 blah. You have a lot of stack call already. Then you're done, yay. Fib of 2, right? If fib of 1 plus fib of 0, you're done. Then fib of 3 is fib of 2 plus fib of 1, so you add again fib of 1. And over here, you still have fib of 3, right? Not too bad yet. You finish with fib of 1. Look at this, right? Imagine, let's say you finish up to say fib of 10. Fib of 10. And you finish with fib of 9, fib of 8, all those things. What is fib of 10? Fib of 9 plus fib of 8. Fib of 8 grows. Fib of 8 would then grow another more. So at the end of the day, Fibonacci is a bunch of like calling this like a function call that's really, really, really deep, right? And this right side also call again. So this is say 45, right? This is 44, 43. 43 would then call 42 and 41, right? 41 would call 40 and 39. 42 would then call 41 and 40. You see how the number of function calls grow pretty much exponentially, right? So at some point, you're gonna allocate so much that is that overflow, so much variables between each function call because of that, right?
Yeah, it's fine. It's before really. By the end. Oh.
Yeah. 1 million is a lot. There's a lot. So here is the general, if you can somehow visualize the stack frame with a human figure, right, as in a human understandable figure, the right side is what it would look like. That's is there's a current stack frame, which is top to bottom, right? Top to bottom, which is top to bottom. Uh, this this is the current stack frame here, right? So it will build arguments, right? It will actually have access to, if you have say more than 6 inputs to your function call, the 7, 8, 9, 10 will be on here, the blue part. The blue part on the slides. So, oh my bad, sorry. This argument building is for you to call the next function. The argument for this blue function will be stored here. Arguments that are greater than 7 will be stored on the stack. Right? Then you put in the return address. Now that I make a mess of this slide, let me clean it up and do it again. Sorry. There's a current stack frame and the color stack frame, right? The color stack frame. The color has to do two things. Put in the return address. So let's say F call G, right? F call G. This is F. This is G. F has to make sure you put in the return address. Also have to make sure it organize all the inputs that are greater than 7 on the stack. So that's it. That's it for the function F, which call G. So for function G, if you need anything that cannot be kept in the register, let's say you have so many variables, right? Put it on a stack. And put it on the stack. You can save register and you can put in the old frame pointer, which is RBP. So that's an option for you to actually store the old RBP. Any questions so far? Basically, with the function G, let's say you are currently in function G, RSP will point to the top, RBP will point to the bottom. Okay. And the reason why you can actually store old RBP is for your convenience, because let's say you finish your function call, you return, you can then update the RBP with this value. It's just for convenience because it's there. You save it, right? And here's the example. I just want to increment, right? I have the pointer P, I have value. I want to add, this is what I want to do, star P plus val. This is what the code wants to do. I expand it so that each line here corresponds to each line in assembly. Same function, right? The yellow box is in C, the green box is in assembly. What you can see here is the first line is, well, we have long x equals star P. P is a pointer, it has the address, right? The first input is in what register? You can look at the assembly and you can tell me. That's the first input, right? RDI is the calling convention. The first input will be an RDI. So the address, when you have parentheses over a register name, it means treat that value as an address. Look at that address wherever RDI is pointing, move the value of that address to RAX. So this is basically means x equals star P. Right? Then the next line is I say x plus val is y. X plus val is y. I add RAX, which is right now, this is x, right? RSI is the second input, so that's val, right? You add them together. And then write the results, right? write the result to store P. This is the result, RSI, because you just add RAX and RSI together and write it to RSI. So RSI takes X plus that. I write this value back to wherever P is pointing. RDI is P, parenthesis RDI will point at that address. So you write the value and then you return. You return X, right? You return X, which is RDI. It's already there in RAX. So you're fine. You don't have to do anything else besides calling return. RAX, as you can see here, you go look at the code again, you see that RAX will take in the return value, which is X. RDI is the argument P. RSI is the argument val. And then after your computation, RSI becomes Y. Right? Another example, right? Called increment, a totally different example. Sorry for the name confusion. It's another program. I have V1 is 15 to 13. V2 is the increment, which basically called the earlier function, right? Earlier function. This add V1 with val, then val is right now is 3000. And you return V1 plus V2. So this is what will happen, right? Called increment. Look at how I prepare the stuff. So the first thing I have to do, what is RSP? Second input, right? Oh no, sorry. RSP is a stack pointer. My bad. RSP is a stack pointer. RSI is the second input. RSP is a stack pointer, which is this, right? This is, initially, it looks like this. You have the return address of the function. You subtract this by 16. What happened? What happened if you subtract RSP by 16? You go down 2 boxes, right? You make 1 box and another box. So this is the new RSP. You store 15 to 13 with RSP plus 8. So this corresponds to RSP plus 8. RSP is here, RSP plus 8 is here. You move, right? Move the value here to 15 to 13. So that's the red part for now. I'm gonna move the slide. Any questions so far? This is the red text on the slide. I'm gonna move to the next 2 lines. All right, so we are done with the first line. We're done with the second line in assembly. We're going to the third line. The third line, move out 3000 ESI. Why do we have to do this? What is ESI? What is RSI? RSI is our second input, right? RSI is our second input. It's because the calling convention, somehow we have to make sure that this second input has to be stored in RSI. Has to be stored in RSI. The reason why we use ESI versus RSI is ESI is for 4 bytes, RSI is for 8 bytes. How many bytes do we need to represent the 3000? Well, it's log of 3000, right? Which is around, it's, so log of 1000 is 10 bits. 3000 is within 16 bits. So it's less than 2 bytes. ESI is a little bit more power efficient in computer. Basically, you just move around with only 4 bytes of data. So the compiler, when you run GCC, would convert this to ESI instead of RSI. You can actually use RSI here, so it would result similarly. It might consume a little bit more power. That's all. Great. So you store 3000 for the second input. This is the caller, right? The caller, the function that calls another function. They prepare the input. So this is the first thing you prepare. The first input is VI, right? V1. Where is V1? right here. 15 to 13, that's where VL1 is stored. So what you want is you want to make sure the first input or RDI takes in this RSP plus 8, which is exactly what we do here, right? You take basically LEAQ compute the address given RSP plus 8. So first node, move out 3000 ESI. It works for 4 bytes data. As we said, well, we know for sure 3000 is within 4 bytes, so let's use 4 bytes. It's a little bit more efficient. Second node, LEAQ compute this. Right? So you store that value into our target. Target is RDI. So after this line, RDI, sorry. After this line, you see that RDI would have the address of V1, RSI would have the value 3000. Then you call the function, right? So the calling that function is earlier thing, which is you add the two numbers together. If you call the function, this number will get updated. Basically, we add 3000 to that, right? And the return value, right? Because RDI is this, RSI is this, you add RSI to this address. So 15213 becomes 18213. When you return, RAX has the return value, right? What happened here? You want to do V1 plus V2, right? What is V1? 15 to 13. What is V2? 18 to 13, right? So over here you have 18 to 13, which is the updated value. If you remember our increment function, which is defined here, a few slides ago, RAX is the old value, should be this. So if you look at the definition of increment, right? So do you mind if I go back a few more slides? This is increment, right? You return X, which is this. You return this. So at that point, this value is 15213. Basically, the return value of this function would be the old before you update, the old value before you update. So over here, right, when you call the function, this gets updated to 18 to 13, but you return 15 to 13, which is exactly what you want to add. Okay? You want to add 15 to 13 with 18 to 13. So after you call increment, you basically do that. V1 plus V2, how do you do that? This is 15 to 13. This is 18 to 13, right? Because you know RF is your return value, and you know that 8 RSP is this, 18 to 13. Add them together, yay, right? That's it. Basically, you after this, RAX will have V1 plus V2. Because we already said it, right? We add here the 18 to 13, write the result to RAX. So now RAX, after this, RAX will take the addition of the two numbers. What's the next thing before you return? You update the stack pointer. The stack pointer was here, the one at circle. You want to make sure it go back here. You want to make sure it go back here. Anyone wanted to guess why? Why? Before you call return, it has to go back to here. Yeah, to make sure that right now stack pointer point to the return address. Otherwise, when we finish this function call, it don't know how do you return, right? If you don't update, if you don't have this add queue, right? So over here, let me show this part, right? You just want to return. This is what you want to do. You just want to return. RSP is right here. If you don't update the RSP, it would use whatever value is here, whatever value is stored here, which is unused, right? That becomes your return address, which is wrong. So you want to make sure you update, go back here. You go back here and you return to that address, so you can continue running the function. Okay. And that's it. You return and you basically go to that address. RSP move one step up, which is here. All right. So in summary, right, a few important points that you will want to be careful about. The stack is the right data structure to maintain function call. Why is that? Because you call function within a function within a function. Each time you call, they grow on the stack. When they're done, you can collapse the stack. Recursion basically is handled by a normal convention. Basically, you can safely store any local thing you want to store. For example, that 15213 thing. I use my stack to store 15213, right, inside the stack. And that's safe for me to do because I own that window. Then make sure the return value is in RAX before you return and call RET to return from the function call. Make sure the stack pointer points to the correct return address. And that's it. Treat of a treat pointer like just a bunch of addresses. Okay. So that's it for today's lecture. Yeah.
So it means like all the case that in the assembly, the return value will be the RAX for all case.
Exactly. Yeah. I mean, because I love to always joke computer are stupid. What makes it brilliant is how you program it, right? So that's the fact, right? The way you design a computer, because it's just a bunch of electrical signals, you have to make it as simple as possible. That's why we would, hey, I'm gonna make that assumption that say, if I use RAX, that's my return address. It's created as an assumption so that you can use it to return something.
Also, it's a protocol.
It's a protocol, exactly, yeah. So now that actually we are done with assembly, the next part of the lecture has to do with more like what we call computer organization beyond the CPU. Anyone here buy a computer before and saw the processor spec that say L1 cache is these many kilobytes, that's these many megabytes of L2 cache and L3 caches? We'll talk about what are those things. We'll talk about how to make your program faster. Right? We'll talk about how to make data access fast. Most of the time, the memory is the main bottleneck in your program. It's what is slow. How slow? About 30 times slower than just accessing register. So it's a lot slower. We'll talk about how the OS prevents any illegal access, and instead of having you doing the illegal access, throw you segmentation fault. So it's better. I mean, trust me, it's better. Why? Let me compare two cases. If you don't have seg fault and crash your program, what if you modify the OS data and crash your laptop? Right? So it's safer to throw seg fault and say, hey, you cannot modify that data because you didn't own it. I'm gonna crash your program. At the same time, I'll at least make sure Windows, Linux still run. Right? So we'll talk about how DOS prevents it. This is called virtual memory. We'll talk about virtual memory and its benefits. And before we leave today, we have a midterm survey. It's already on the announcement. I would really, really, really appreciate feedback, especially for every one of you who haven't taken data structure and haven't taken algorithm. I really want to make sure I know exactly which are the gaps I should fill in, or if I should take out some of the components, and maybe we'll discuss among Ajahn Kanat and Ajahn Sansern on like, okay, for the next class, should we migrate some of this to the next class, or should we kind of retain this in this class? So this survey should be really useful for your friends who will be taking this class in future semester and yourself, because I'm basically asking how much time you spend on assignment 1, 2, and midterm, so that I can adjust assignment 3 and 4 and the final accordingly based on the response. I don't want to commit mass murder again. Definitely not fun. I did realize that. And let me stop the recording.